Hi class, we are on to section 8.4. We're going to cover de Moivre's theorem, which is powers and roots of complex numbers. So in this section, we will talk about taking a complex number, raising it to a power, which could be a fractional power, which, as you know, a fractional power is a root, right? So like 4 to the 1/2 power is same as square root of 4, right? So we're going to really just be talking about how to raise a number to a power, right? Whether that's a fractional power or a whole number power. Okay. So for de Moivre's theorem, we're going to take a complex number that is in our polar form, right? R equals cosine theta plus I sine theta. And if n is any real number, so in this case, a rational, a whole number, an irrational number, right? Then raising this polar form to a power has this equation, basically, right? So you take the r and you raise it to a power, and then your cosine theta, your sine theta, your trig terms, your trig functions, they're basically n multiples of theta, right? So I have r to the n times cosine n theta plus I r to the n sine of n theta. Okay, so again, this translates very well into the compact form, the cis form, and it is the same thing as if I were to have a plus bi all to the nth power, because remember, this is just the polar form of a plus bi, right? So now let's take this formula and yet let's use it in a quick example. So again, you take the radius, you raise it to the nth power, and then each of your thetas inside of your trig function are multiplied times that power you are raising it to, n, right? So for our first example, we will use the complex number I plus I root 3 to the 8th power. And so what we need to do is first we are going to write this in its polar form, right? We find the radius, we find the angle. And then once we have that, we can now take that form to the 8th power, and then we will just take the radius and the angle, and we will follow the formula. Okay, so again, right, following the process, we write this in our polar form. So doing the work yourself, you can verify this, that we should get a radius of 2, and that our angle should come out to be 60 degrees, right, because you're basically going to get 1 squared plus the square root of 3 squared under a square root. So when you add 1 plus 3, you get 4. Square root of that is 2, right? And then you can use your tan inverse of root 3 over 1 to find your cosine, right? To find your angle, and then that's how you figure this out, just in case you don't remember how that worked. So once you have these values, right, we can now apply our theorem, right? So we know it's the 8th degree, so we will take 2 to the 8th, and 60 degrees we will now multiply times 8, right? Okay. So here we will apply our formula, so 2 to the 8th power, 8 times 60 degrees, 8 times 60 degrees. That gives us 480 degrees. And so, of course, we need to find the coterminal angle, right? So 480 and 120 are coterminal. So we can replace 480 with the 120, and that gives us this value, right? So again, these are our standard sine and cosine values. We don't really have to plug those into the calculator. We should know those from the unit circle. And then now we just apply this. We actually have to finish this out, so we're going to divide 256 in half, divide it in half again, and then just write it times root 3 because we need exact values. So we get negative 128 plus 128i root 3, right? So that's how we find the roots of a complex number, okay? For a positive integer n, the complex number a plus bi is the nth root of the complex number x plus yi if a plus bi to the n is equal to x plus yi. So we're basically doing the opposite of what we just did over here. Okay, if I were to take negative 128 plus 128i to the square root 3, and I took that to the power of 1 over 8th, right, or the 8th root of this, this would be the value that I would get out, right? So I can take this to the 8th power and get out in a complex number. I can also take a complex number and take the 8th root of that, or any square root, really any root, and come out with another complex number, right? So again, these are our number systems. They behave like real numbers, right? If n is any positive integer, right? Let's say r is a positive real number and theta is in degrees, so our radius and our degrees. Then the non-zero complex number, r cosine theta plus I sine theta, has exactly n distinct nth roots. So for instance, if we're thinking about comparing these complex numbers to the standard real numbers, if I were to take the third root of 2, third root of 2 will have 3 values, okay? Now that doesn't happen in the regular real number system, right? But that does happen in the complex number system. If I take the third root of a complex number, I'm going to get 3 different answers for that, okay? And so that's how the complex numbers root-wise is a little bit different than the real number system, okay? So again, if I take the nth root of a number, I will have basically n values that come out, okay? And so those values happen at different angles, okay? In their polar form, I'll get different angles around the unit circle. I'll get n of them actually, and each one of those angles are calculated by this formula, okay? You take your original theta for the number you were trying to take the square root of, you add 360 degrees to it, you divide it by the number of roots you have, and you're just adding multiples of k to the 360 degrees, because each time you're going to land somewhere else on the unit circle, right? And you basically do that n minus 1 times. So we go around the circle a few times, and each time we'll land on a different part on the circle, and each of the points that we land on represents a different root of our complex number that we're taking the root of, right? So we go, so this k value is what allows us to get different values, the n different roots that we want, okay? So for this, okay, I know we're talking about in degrees, but generally we want to do this in radians, okay? If we're in radians, we cannot talk about this formula with 360 degrees times k, right? It needs to be transformed or changed into its equivalent, which is 2 pi, right? So instead of going theta plus 360 degrees, 1, 2, 3, up to n minus 1 times, it'll be theta plus 2 pi, 0, 1, 2, 3, up to n minus 1 times, okay? Right? So it'll change into this form, right, instead. Okay. So for our next example, we want to find the 2 square roots of 4i. So we're going to take 4i, and we basically just want to take the square root. If you remember, as I said earlier, 4i means that you have 4i to the 1/2 power, right? So there should be 2 roots there. So we want to write them in rectangular form. So not the polar form, but the standard complex form, right? So to write 4i in our trig form, since our formula is all about, again, all right, let's go up a little faster. The trig form, we got to put this into our trig form first, and then we can change, oops, too far, okay? Then we can change things. So again, my radius here is going to end up being 4, and the angle that it creates is pi over 2, because this is strictly straight up 4 units on the imaginary portion of the complex number plane. So it has a radius of 4, and the angle is pi over 2, right? It's a 90-degree angle, okay? Radius is 4, theta is pi over 2, and we want the square root, so there's going to be 2 roots. So we're going to follow our formula, right? So the square root of 4 is going to be 2. And our alpha, now, we have to find the 2 corresponding angles. So we follow the formulas that we just had, right? So theta divided by 2, and we're going to add 2 pi over 2 k times. So first k is 0, the second k is 1, and that's it. Remember, it's it ends at n minus 1. So in this case, n is 2, right? So pi over 2 over 2 is the same as pi over 4, right? Here the 2's cancel, so we'll basically have pi over 4 plus 0 for the first k, which is k equals 0. And then for the next one, we will add 1 pi onto that value. Okay, so for the first one, for all of our alphas, it's pi over 4 plus pi k. And since there are 2 square roots, which is again why n was 2 in this case, right? K is 0 and 1. So for k equals 0, we're adding nothing, and my first angle is pi over 4. Okay, and when k is 1, I'm just going to add pi to pi over 4. So I'll have 5 pi over 4, right? So using these values, it basically cuts my unit circle, or my circle of radius 4, in half, with one of the roots lying at pi over 4 and the other one lying pi away at 5 pi over 4. Okay. So 2 cosine I sine pi over 4, right? 2 cosine I sine over sine, or 2 cosine I sine 5 pi over 4. Okay. So again, when we write this out into our rectangular form, we're just writing the root 2 over 2's that I have here, right? And we simplify times that power of 2, so I get root 2 plus I root 2. Here will be the same thing. This should say 5 pi over 4, I don't know. So again, I didn't make these PowerPoints, so this is an error on the PowerPoint given to me by the author, right? So I just kind of adjust these a little bit. But regardless, right, it's still pi over 4. It's just at a different value, different quadrant. So we have a negative here. So I have root 2 plus I root 2 and negative root 2 minus I root 2. And then if we were to graph this on the circle, you would see that these are a distance of pi apart. Not a distance of pi apart, but an angle of pi apart on the circle of radius 4. Okay, so for our next example, we want to find all the fourth roots of negative 8 plus 8i root 3. Okay, and again, we want to write the roots in rectangular form. So this one is a little bit more work, because instead of finding 2 roots, we're going to find 4. But it's the same thing, right? I know that I was talking about the graph of the last example, but we will be graphing the roots on the circle in a couple of examples down from the one we're at now. So it'd be a little bit easier to visualize what it is these things actually look like, right? So right now we're just kind of going with the base calculations, which is finding those roots, right? So we'll worry about graphing them later, right? So again, the first step is to write this in the polar form, right? So I need to find my radius, which is root 256, which is 16, okay? And I need to find my angle. So again, I use 8 root 3 over negative 8. Those 8's cancel, so I find theta by using tan inverse of root 3, okay, which is 120 degrees. So negative 8 plus 8i root 3 has a radius of 16 and a cosine measure of 120 and a sine measure of 120. So I can throw this into my short form or my standard form for the polar form, which is fine. Okay. And if I want to find the fourth roots, I need to find the fourth roots of the radius, which is 2, right? 2 times 2 times 2 times 2 is 16. And then I have to multiply my theta times 4 a few times, right? Or 1/4, I should say. Apologies, right? So each of my alphas follows this form. So again, the first k is 0. So that's just 120 degrees divided by 4, or 30 degrees. And then I will start to add 360 divided by 4, or 90 degrees, once and then twice. And so I'm starting here at 30, and then I'm counting 90, another 90, another 90, another 90, until I finish out my circle, right? So there are 4 roots. So k equals 0, 1, 2, and 3, right? If k is 0, then I'm adding nothing to this, and I'm just at 30 degrees, right? The next 90 degrees more will bring me to 120 degrees, right? So for k equals 1, and then I'm 90 degrees more than that, right? So it's basically the standard unit circle tilted by 30 degrees. Everything is off by 30 degrees, right? So 210 instead of 180, and instead of 270, I'll be another 30 at 300, right? And then that's it. Okay, those are my 4 degrees. So using these values for alpha, my 4 roots, I can now compute, right? It'll be 2 cis 30, 2 cis 120, 2 cis 210, 2 cis 300. And then, of course, we want to calculate all of those into our rectangular form, because that is what they wanted us to do, right? Write those in rectangular form. So first we want to write those into the polar form or the trig form, and then we can go from there into from our trig form into our polar form, right? So we'll do this one at a time. So 2 cosine I sine 30, right? So again, we're just looking at the special values, the cosine values and sine values for 30 degrees, right? So that's root 3 over 2 and 1/2. Multiply that times the radius, and we get root 3 plus I, right? We're going to do that for 2 cosine 120 plus I sine 120, right? And so again, we just pull it into the rectangular form. So here things are pretty much the same value, right? Except for cosine is negative and then sine is positive. So I should get negative root 3 plus I, right? Because it's the same thing, but now we're just kind of over a little bit on the quadrant 2, right? And at 60 degree measure, I guess. So that swaps it around a little bit. 2 cosine I sine will just be, again, so that has a reference angle of 30. So that will be the same as this, but it'll be, this one will be the negative root 3 plus I, right? Minus I as well, because it's in quadrant 3. And then same thing here, we just find the reference angle and find the rectangular values. Okay, so again, we're familiar with doing this part because that's what you've been doing for the last section. Just in this section it's a little different because this is now the last part of a bigger problem, right? So these are my 4 roots for that one single complex value that we started with, okay? And on the graph, as I said before, it's rotated by 30 degrees, right? So it's kind of like this standard axis now being rotated 30 degrees. Since there's 4 of them, they all are going to be equidistant on the circle, and so they're all 90 degrees apart. That's why it looks like the standard unit circle just rotated by a 30 degree angle measure, right? Okay. So the roots again are equally spaced about the circle, 90 degrees apart, since 9 equals 4 and 360 divided by 4 is 90 degrees, right? So if we were doing a 5th root, all of these roots, there would be 5 of them, and they would be equally equidistant around the circle, right? And they would all be whatever 360 divided by 5 is, right? And so that's the way that these work, right? So let's do another example. So we're going to find all complex number solutions of x to the 5th minus I equals 0, right? So now we have an equation rather than just find these roots. It's not that much different, right? We single out the x and then we take the 5th root of both sides, okay? So we're going to graph them as vectors in the complex plane, which is very similar to what we did here, right? We're going to graph each one along the unit circle, not the unit circle, but the circle of radius, whatever it is that we're going to be using, right? In this case, notice that the radius is 2, and that's how we're going to graph these in the complex plane, right? It's really just a circle. So again, we're going to move this over, and then we're going to take the 5th root, okay? And here there's only one solution because this is positive, not negative, right? Which is 1, so we basically have 1 5 times. So what we want to do here, since we're trying to write these in vectors in the complex plane, we got to write 1 in its polar form, and then do what it is that we're trying to do, right? So here r is 1, the angle is 0 because it's on the x-axis or the real axis, right? So if we write this in polar form, this is what it looks like, okay? And then we can take the fifth root, right? And then go around our circle 5 times, right? So 360 divided by 5 is 72 degrees, right? So we're really taking 0 and just adding 72 degrees around a radius of 1, right? So the first one is k is 0. So we have 0 degrees, okay? K is 1, so that'll be 72 degrees. K is 2, so that'll be 144 degrees, right? And so forth through our 5 actually, right? Because we're cutting 0 calculations. Okay, so we're basically on a circle of radius 1 along these angle measures. Okay, and so all of these are equidistant apart on the unit circle, right? And those are the 5 roots of 1.